All right, if I'm not mistaken, then we are live for the second time today, and for a very exciting piece that we've got planned. So, good morning, good evening, good afternoon, good night, good everything, wherever you are in the world. We are very excited to have you here, and I'm sure you're all very excited too, because this is going to be a masterclass in the Kevin board. We've got the. I'm sure he's got plenty of those planned for you. This is definitely obviously the strong point of presentation. This is the VM. This is the moment, the one. Let's say. How else would you describe it, Kevin? Is that that's about where you're at? This is the moment.
Yeah. I think of course, the ability to host your nodes and go through that process is important. But what happens is, if you look at various layer ones out there today, or even the layer two solutions, you see a lot of forking going on in the virtual machine side, because that's a very ambitious step to take when you're building a layer one solution. And the virtual machine is such an important and critical part of the protocol, where if you don't have your virtual machine set up in a way that it can scale and it's secure, it doesn't really matter how much of a good consensus mechanism you build. The engine in itself of the car uh, you know isn't strong enough to support the race. So I think my expertise being in virtual machine, and why we decided to have our own virtual machine instead of forking someone, we'll go through that today, and I'm very excited.
Yeah, absolutely. It's funny, the car analogy. Obviously, we were just talking F1, so very pertinent as well. The engine, obviously, it's what propels everything. It's what everything's based around. If you don't have a good engine, obviously, you're not really even in the race. So excellent to know that we have. I suppose you would call yourself the leading expert in the L1X VM. So without further ado on that, let's dive straight in. I'll hand over and let you get started, because I know we've got a lot of content to go through as well, to really give an overview of what that looks like, how it all fits together, and any of the nuances, I suppose, that we can dive into that will help the community understand, but also from higher levels as well.
Yeah. So I'll just pull up my Miro board.
Of course.
Yep.
Fantastic.
Yep. Can you see the board?
Yes, sir.
Awesome. Okay. So what we'll do is, we'll have a relaxed session this time, because explaining the VM requires understanding each and every component. And I think anyone watching this, thank you for taking the time. And this 1.5 hour that we are going to go through is going to be so productive that, put it this way, if you are into Web3 and your investment strategies are there, if a project is talking to you about itself, and you have a few questions on the VM, and the way the answers are given, you can kind of see through it, where is this project going to be sustainable or not, right? From the utility standpoint. So I think this 1.5 hour, we're going to have fun, but more importantly, we're going to learn a lot about the L1X infrastructure, but also the virtual machine, in general. So what we'll do is, we'll go through the recap, basically on the node framework and the contract types that we have. I'll try to keep it as less technical as possible, but at places it will get technical, right? In the part one, we'll go through the compilation flow of the L1X VM and various decision markers, where, based on what type of contract, what type of transaction certain activities happen. We'll go through the execution flow. So first we'll look at the compilation, we'll look at the execution, and we'll also maybe just briefly glance through the contract executor. The contract executor basically is a pretty complex graph. So if any developer wants to have a look at it in depth, they can do that. And at the end, also, we'll have a look at the L1X VM and EVM contract flow. How do these both work together as well? So this is the part one. In the part two, we'll go through the opcode table and the fee calculation. So, how does the fee get calculated on the L1X infrastructure? And also in the part two, we'll go through the database manager and storage instructions. Like, for example, if there is any Solidity developer here, you've got the store and sload opcode in EVM, where they cost a lot. So there are certain ways on how you can design your contract that can be more efficient, and we have our own ways of doing it as well. So we'll go through that in part 2.
Absolutely jam packed, as everybody can see. So yeah, let's strap in. Let's get after
it. All right. Now, your VM that you have on your node, the easiest way to understand that is without your VM. So how do you know how important something is? You just remove it, right? You'll know how important that is. So if you did not have a VM, you would not be able to execute contracts in a way that everyone gets the same answer, right? So if you have 10 nodes running and you did not have a virtual machine and you tried to do something without the VM, you could get different answers every time, right? And VM provides a deterministic factor in executing things on the blockchain. And if you can't execute things in a deterministic manner, then the state management in terms of how you update your databases, will not be validated. So your tenet of blockchain, falls. And this is why a virtual machine is very important. It's the core or the brain, I would say, of a blockchain network. Now, for those of you who missed it in the consensus mechanism AMA, we have 4 different types of clusters, and all these 4 clusters use the virtual machine that we have. For example, the L1X, except the EVM, all of them use the L1X VM. The L1X EVM cluster uses the L1X EVM instance to execute transactions. There are 3 different contract types. So we have L1X VM contract, we have the L1X EVM contract, and XTOC. What's the difference between L1X VM and XTOC contract? The difference is if you are using the XTOC nodes to bring in information and register it with the L1X VM, that is classified as an XTOC contract because that particular contract interacts with the event listener or the XTOC node and is designed specifically to understand the event listener node's infrastructure as well. Your L1X20 contract, that is your fungible token, or L1X NFT contract, those all that do not use the XTOC infrastructure can fall under L1X VM contract. And the developers that want to build with Solidity, they can go and deploy their contracts on L1X EVM. Now, of course, you can have all these 3 contracts working together. So it's not necessary that only L1X VM contracts can interact with each other. You can let your L1X VM, EVM, and XTOC contract interact with each other using the same infrastructure. Now, let's probably look at the compilation flow. Now, before I explain the compilation flow, it's important to understand what compilation even means, right? So let's say you get a task where you have 2 numbers to be added to each other, and you need to add these 2 numbers on the blockchain, right? So 2 users are going to give their inputs from 2 different parts of the world. They can't see each other's information before they give it in, and you send a request, it goes to the blockchain. Now, what happens over here is in your front end, when you are actually inserting that number, there is a specific contract that is deployed on the blockchain. Now, the blockchain doesn't understand the contract as a developer writes it. So the difference in understanding this specific function that I need to accept 2 numbers and add that in the computer language is where compilation is required. So when a developer writes and gives it to the compiler basically acts like a translator between the developer and the computer, saying that this is my code, translate it for me where the computer can understand that. And in very essence, even that is like interoperability. So when there are various protocols saying that we are interoperable, they can mean a lot of things, right? They could say we are interoperable within our infrastructure versus even outside the infrastructure. So that is what compilation is. And when you are compiling things from the source to the destination, there are various permutations and combinations. Like Solidity code is compiled differently, Rust code is compiled differently, and they're compiled to understand like what type of a computer it is. So in that way, I need to do my compilation. I can't take the same code that I give it to a browser and go and give it to an IoT device, right? It's not going to understand. So what is the destination architecture in the compilation or object code is where compilation strategy fits in. Now, how does the L1X compilation flow work? We have Rust code where the developers are actually writing smart contracts in Rust, and the Rust code gets compiled to something called as WebAssembly. Now, how does the Rust code get compiled into WebAssembly? The Rust code first goes through something called as HIC, or high level intermediate code. It goes to something called as low level intermediate code, and then you get the WASM bytecode. Now, what you need to understand from here is the low level intermediate code. Now, this low level intermediate code acts as a standardized translator, meaning if I have 5 different people speaking different languages and I have 5 different destinations, if I receive one and if I need to give it to somebody else, if you do it directly from A to B, you would have 25 different combinations you need to work with. So to reduce that combination to only 5, the low level intermediate code understands that. So it can accept it in some language, understand what is the destination, and translate it based on that. So this reduces the overhead of how and when you need to go and compile something for your destination architecture. This part here is not proprietary to anyone. So there is something called as Rust C compiler. Your Rust code directly compiles into WebAssembly. So all the blockchains that use these kind of compilers, they have not done anything proprietary. They've gone and tweaked around a few things. They've forked it basically. Now, what is the benefit of this code and what is this code, right? WASM code is portable, right? It is, it's basically built for the browser environment as well. So if you are actually executing things on the browser, you may use JavaScript. But certain programming languages like C and Rust cannot be executed directly on the browser. And this is where WASM comes in. The WebAssembly code can be executed on the browser. Now, what is the difference between executing JavaScript versus WebAssembly on the browser for everyday people? Your games, the Unity engine, is built using C. So they can't use JavaScript straight away to execute because it's very resource intensive. So whenever you think about resource intensiveness and security, that is where WASM is used as a leader to JavaScript. If you just want to build a simple website, you don't do it in C language. You can do it, using Node.js or JavaScript. So this is where we need it to be portable. So it's very portable. It can be ported across various web browsers, and you can use it as well. And Polkadot uses WebAssembly. I think Near Protocol also uses WebAssembly, where it has been taken out of the browser environment and it has been deployed into virtual machines because it's like a near time, machine language executable. So it's like pretty quick, right? The size is small. Now, why is the size small, right? What does this even mean? Now, when you have something where your computer tries to execute that bytecode, it has to understand that if I am going and trying to execute these things line by line, I need to know the location in the storage. So when I need to know the location in the storage, there are 2 ways to do it. One is ahead of time compilation, where you do it before you give it to the computer. And one is just in time, that you do it right on the computer straight away. If it is reduced in size, you don't have the location for that initially. But later on, when you are doing it just in time, you need to have that location. So WASM code does not have the location. That makes the size smaller. If you want to understand an analogy behind this, say for example, you are planning a trip from point A to point B. It's 100 kilometers, and at every 10 kilometers, you need to write down a certain code, right? Now you have 2 ways to do it. One is you wait for all the 10 codes to come to you, and then you go ahead. So you're not waiting then, right? You're executing it. But then your wait time is bigger. Now the wait time here is how much you need to carry. So let's say one code is given to you on one brick. So you got to take 10 bricks and carry along with you. On the other hand, what I will tell you is every time you reach a spot, I will give you one brick and you take it forward with you. So in this way, you're not waiting, but you're faster, but you'll have to wait at that pit stop to get that brick. The difference over here is WASM code is lighter in size, but it takes more time to execute because it has to get that brick one after the other. eBPF bytecode is bigger in size, but it takes less time to execute because it's carrying all the bricks together with it. So it doesn't have to wait in that process. So, of course, it's a reduced size. And browser-based execution, as I mentioned, it can be executed on the browser as well. Now, why have we not just used WebAssembly then? If Polkadot is using it, Near Protocol is using it, and this excites me because this is where I can throw in the visionary aspect of things. I believe that we are in this cycle of overloading or delegating execution responsibilities, where before a single computer was executing it, now 10 different decentralized nodes are executing that. But let's just take two examples, AI and IoT. A lot of the computation has to happen on the device, right? And second, with IoT, even device execution is very important, like edge computing. If these industries need to move towards a secure Web3 infrastructure, you can't overburden the decentralized nodes with this execution time. It has to come back to these IoT devices, let's say mobile devices, refrigerators, your web browser. Now, the problem is these devices don't understand WebAssembly, right? And if you want WebAssembly to be used because it's the next big thing in terms of adoption, then we also have to consider the fact that WebAssembly cannot be used in edge computing devices. And this is where we need to take the WebAssembly bytecode and make it eBPF compatible. Now, if you see, we have the LLVM code here. So how is this different to this particular code? It's different because when you build a smart contract and deploy it, that same smart contract in its same security fundamentals have to be executed even on those devices. So if I go back and try to compile the same smart contract into another format, maybe there are security challenges that may happen. And this is why we decided to build a compiler that takes a WebAssembly bytecode and compiles it into eBPF bytecode. So this process of going from WebAssembly to eBPF, we have to handle one thing, which is we have to take the WASM bytecode that was generated using the Rust smart contract and build it into LLVM IR. This LLVM IR is the same as this one over here, in essence. But when we take the WebAssembly bytecode, we have to translate and compile that same information in a deterministic manner into LLVM IR. And why LLVM IR? Because if I am executing a smart contract on the browser, this is like future version 1.1. If future version 1.2 is with IoT devices, then future version 1.1 has to carry forward the same smart contract onwards. And this is where LLVM IR compilation allows us to go and, based on the destination architecture, recompile that code into that format. So if you wanted to compile it into eBPF, you could do that. If you wanted to compile it into low-level language code directly, you could do that as well straight away. This allows us to provide scalability because you don't have to maintain multiple versions of the contract for multiple types of devices. This helps us to even take into consideration, maybe this is the only chain that IoT and interoperability can work together. So when you take a concept like I am executing a certain smart contract on the node, but I am also delegating responsibility to an IoT device for this smart contract to execute. But the IoT device depends on external data coming in from manufacturers. Then, to achieve this security and scalability, this compiler that translates WebAssembly into LLVM IR is very important. And I'm glad to say that we have been, the contract has been, audited by Hashlock, and we have found no high level, errors there. It's all code restructuring and commenting. And Monday we have an AMA with them to go through that as well. So it allows us three important things. It reduces the burden on the nodes because there is only that much Web3 will scale, like in the next 2 years, 1.5 years. And to really scale the utility of the infrastructure, we will have to look at alternatives where we remove the barrier of computation from the nodes and delegate it back to the devices in an accountable manner. And that's where zero knowledge will come in as well. Environment specific execution. So instead of you going and recompiling your smart Rust code into the same smart contract, you can use the same smart contract and compile it back. So you're going from smart contract compilation to a smart contract, and from one smart contract to the same smart contract for a different format, right? And you could have the same version deployed across multiple places and keep track of it. That's important because if certain types of smart contract need to execute on IoT devices versus your computer and the node, and they are three different ones, then you need interoperability for that as well. So in this case, you could use the similar state management of that smart contract in one infrastructure. Now, it's future agnostic, of course. When we decided to build the VM, we could have easily forked EVM. It would take me like 3 days, and we could put our consensus and off you go. But we had to make this decision because the problem is if we release it with a VM and then later on change the whole infrastructure, I don't know what challenges that can bring in the future for the applications that are building with us. And to provide this long-term pathway, this infrastructure was very important. And we spent like a year building this technology. Now, once you have your bytecode, you take that bytecode and you execute it on something called as a runtime. A runtime is basically an instruction set or an opcode set that executes one by one. And the difference over there is your runtime can be register-based or stack-based. Now, what's the analogy? If you are looking at WebAssembly and stack-based architecture versus you're looking at eBPF and register-based architecture, let's take an analogy of a kitchen, right? Let's say you got these plates stacked up at one place. Now, every time you need to make something, you need to bring the first plate out, look at the ingredient, put it on the second plate, put the plate back down at the bottom. I don't know if you can do that. You're going to drop the plates, but anyways, let's try, right? You go back to the first plate again, you do the second. So this is like a push and pop, push and pop. So you're taking out one, you're putting back the old plate. Now, when you try to do this push and pop, it's a cyclical process and it's a very time-consuming process. That is WebAssembly trying to execute. And as I said before, if you used an Android version previously, it is slow because it was stack-based. Now, what is eBPF runtime, or what is a register-based system? A register-based system, like if you go to McDonald's and how they've got everything planned out, it's spacious, right? And you want salad, you take it from the first part. You want this, you take it from the second part, and you customize it and you build it. Now, imagine building the same burger by this push and pop mechanism. Yeah, sure, you're taking less space, but imagine the time that it's taking. It's not convenient. You would need to wait 30 minutes, right, for your burger. I don't eat McDonald's, so I don't know. Yeah, but anyways, that's what would happen, right? Now, as I mentioned, the LLVM IR compiled to eBPF bytecode, which runs on the eBPF system. This is the place where the VM then interacts with the node, which is the database. The VM doesn't understand, are you a good person or a bad person? Meaning, if you are telling me that please transfer 10,000 L1X coin and you only have 6,000, the VM doesn't know that. The VM is going to go and try. But what the VM does is the VM knows that these are my limitations. So I need to talk to the database driver and say, okay, give me the address of this person or the balance of this person. It returns back the balance. It does a comparison. Is your balance higher? It's not higher, fail the transaction. So the VM is responsible and relies on the state management to make secure transactions. So the database driver and the on-chain tree is on the L1X node, and that is where the VM remains with. So that's the compilation flow of the VM. So what do you think, Joe? You have any questions so far?
I mean, I don't have any personal questions, but there are a couple that come through from the community that might be worth touching on.
Yeah.
One just around, I'll just scroll back up here. There's one from Fur, of course. Can we say that L1X VM is a polyglot?
Oh, well, I think based on the infrastructure, if you think about it, like the division of responsibility for an infrastructure makes sense, right? And that is why the ability of the VM, where it understands the destination results that you are seeking and adapt to it, I think is important. So maybe it is. I don't know. So maybe it is.
You had all the good questions today, Fur. Since L1X is very new and unique tech than others till date, is the hash lock audit enough?
That's a great question. That's a great question. Okay, good. So if you think about it, the Rust compilation to WebAssembly and LLVM IR compilation to eBPF, this is tried and tested. This is already done in the space. What is not done is the WASM to LLVM IR. Now, this is deterministic, so it's easy to check if something goes wrong, right? In the audit, when you do a translation, you are doing a translation of each and every opcode or stack, if you may want to call it. And the way it's done is you first analyze the code you want to actually translate, you parse it, and then you build an asymmetric tree, right? And when you build this, at each and every step, you know that my WebAssembly executed versus my eBPF executed is giving me the same result or not. And we have done extensive testing over this translation, and it has not failed us even once while we are using it. Like until now, the most, I mean, I'm not saying it because I built it, but until now, the most successful part of the protocol is the WebAssembly to LLVM IR compilation. It has worked since day one.
That's excellent news. And a question from DD always brings the heat on the more dev-heavy sections, I find. This sounds beyond Web 3. Could this be applied onto Web 2?
Excellent question. Very good. The WebAssembly bytecode to LLVM IR and eBPF opens up opportunities for us partnering up with someone like Fitbit, someone like IoT devices like Google Nest. And it is a great way to bring them onto the Web3 infrastructure as well. So this is an unexplored territory that we have. We are focusing on Xtalk right now. But a simple example is you have a reward system, for example, on Fitbit. The more you run, the more rewards you can get. Now, that rewards can be used to buy a product. In this infrastructure, the execution that you are running and you're not duping the device, that can be into a contract executed on the device itself and sent back in a secure way to the nodes. So yes, it definitely opens up opportunities even beyond Web3.
Yeah. I'll just do this once in order. If we've got time for two more before we continue to dive in.
Yeah.
Is it because of this VM that we can scale Bitcoin transaction speeds?
Yes, I mean the VM definitely has, a huge responsibility, and the Bitcoin scalability. I would put the VM in position number 3, because the position number 1 is the ability of the Xtalk infrastructure to be able to listen to information and translate it in terms of like a abstract layer on Bitcoin, like a multi-sig or threshold signing signature. So that's the Xtalk infrastructure. And the second one I would put, we can scale that, is because of the network sharding. So you could have a separate shard executing Bitcoin transactions for us in itself. And then I would put the VM.
Awesome. And then this last question, I think it's about foundations. And then I know I've seen a couple more questions come up, but like I said, we'll keep moving through and we'll come back to those. But this sounds very thought out and connected, but at the same time complex. How did you come up with all of this, and how did it start?
Yeah, that's a good one. I'll take that. So when I was sitting in this room and I was deciding to build my own layer 1, and just the thought of it was where to start, right? So you've got so many parts to it, and the problem is the people who have $300-400 million, they go like, it's like you have an oxygen support and you're trying to climb the Mount Everest. I had to climb the Mount Everest without the proper gear and without oxygen mask. So it makes it very hard. And in that process, you try to find shortcuts. But I didn't want to find a shortcut and copy paste EVM. I know that EVM cannot scale beyond a certain timeline. There is a roadblock. I could see that. Now, what is the other way? The other way is, if you look at the whole history of computing as well, is a lot of the computation has been transferred back to the devices, right? And right now we are now is the time, like if you go 25 years back, you're transferring load or processing power to the centralized service. Right now it is decentralized service or nodes, but it's going to come back to us. It's going to come back on the devices. So how does that come back look like, and how does this process initially work? So going from step A to B and B to C, C to B and B to A, using zero knowledge and cryptographic algorithms, this is where I knew that the VM has to take control of that, at least from the execution standpoint. And that's why I decided to build a WebAssembly to LLVM IR. And I'll give you an example. I was interviewing Egor. So Egor is currently the head of VM, and Egor was working as the senior developer, project manager and developer for Samsung. And he was responsible to build the underlying technology on which the Knox security is built. So all your Samsung devices in the world use Knox for, if you use your Face ID or touch, right? That is where it gets secured. So he was responsible for that. And when I explained to him, he was confused at first. Like, why are we trying to do all this? Why don't we just go from Rust to eBPF or Rust to WASM and get it done with? So then I told him that I give him an analogy. If you're trying to shoot for a movie and you've got a scene where you got to gain weight versus you got to be fit, do the scene where you got to gain weight first, and then, because then you'll have the motivation to lose that fat. Over here, we could have done that part A, but we wouldn't have the motivation to do the part B, which is very important. So that's why I decided to do the part B first and then part A.
Love a good real world Kevin analogy, as that's what it's do you want to continue to crash on, or do you want to take a couple more?
I think let's carry on, and then we'll come back to the questions. Okay, now let's just look at the L1X VM stack. There are not a lot of videos, like even if I went on to YouTube, I mean, even before, there are not a lot of videos on net protocols explaining their VM. There is one video I found on EVM, but they get very intricate into the opcode, right? So this video or this section is going to explain to you the execution flow of a contract. How does that work from development to execution? Right? So first, a developer builds a contract, and when the developer needs to build a contract, he or she uses something called as a L1X SDK. Now, what is this SDK, right? The SDK is like your kitchen where you got everything ready, your ingredients ready. You need to get the meat and then you can start preparing. Now, imagine if you got to go and get ingredients one by one from the grocery store as you need them, right? So the SDK helps you to write the code, and it also helps you to basically compile this code. Now, this SDK allows a developer to understand what are the limitations of the smart contract. Like you can't have infinite loops, you can't have certain floating variables. So this SDK provides the utility and the restrictions around how do you build a contract. Now, how does the SDK leverage, or who helps the SDK? We have something called as an SDK macro. Now, what does this macro do, right? It's like a template. So let's say there are certain low-level calls you got to make to the computer. Like I want to read, I want to write into the blockchain network. Now, these low-level calls, imagine if the developer had to write them into a contract. So what we do is, a developer may say, over here may say, print. This print means that from the macro, it's giving out a low-level information, see out, it can be, and the whole line. So a macro helps the SDK to be user-friendly and provides these templates where you don't have to go and write them again. Because when you write print, you will have like 5 lines of complex code behind it. The macro has the 5 levels of complex code. The SDK only has one word called print. That is where the macro helps templating certain things. And when you compile it, right, we use something called as Rusty. As I went through the compilation process already, I won't go into that again. When you compile it and send it to the blockchain, there are system level calls that you make. Now I'll come to what is a system level call, but this is the compilation process. Now this is where the node comes in, where it goes and deploys this contract on the chain first. I say, all right, let's go and deploy it. Now, once the contract is deployed, right, you can make a smart contract call. The user can make a smart contract call here. But if you want to execute the contract, you got to send it to the VM. The VM picks it up, and this is the interpretation or RBPF. Or the difference between eBPF and RBPF is eBPF is the type of bytecode saying that, you know, I am a nice person is eBPF. RBPF is I bought $10 worth of products for a homeless person. That's executing and showing I am a nice person. That's RBPF, right? Now, what is ELF relocation? When, as I mentioned previously, those bricks that you carry along is like a storage. It's saying that, okay, I have the information I need. So if you're saying, go and change the balance of Kevin at address, but where is this address, right? Where is it stored in the blockchain? That is ELF object or relocation. So once you execute this particular contract in the VM, after you deploy it, the RPPF infrastructure talks to the on-chain tree and execution context. We saw there where the eBPF bytecode is connected to the database. This is that same connection where your VM, which is trying to execute the bytecode one by one, is trying to talk to the on-chain tree. Now, I'll explain as well in point-wise what this means. But from a flow perspective, you use the SDK to build the contracts. The developer doesn't have to worry about SDK macro and sys level calls. Once you compile the code, you deploy the code onto the node. Once you deploy the node and you want to execute it, the VM picks it up. And when the VM picks it up, the on-chain tree that we have currently and the execution context understands what type of a contract this is and goes and executes that. Now, if you see from the RBPF interpretation, we have one process going towards the on-chain tree, one going towards the execution result. And the difference is this. If you have ever built a smart contract on Solidity, you know that storing is expensive. So what is the other way? Emit an event. Just emit. Emit is cheaper. So if you emit an event, it will be like 80% less cost, right, than storing it. If you just emit an event straight away through a message as well, you can emit the execution result, like what is my result as a message. But if you want to store it at the same time, you use the on-chain tree over here. So this helps us understand that in the compilation process, in the node, and in the VM, there are these 3 steps that are followed from the time the contract is compiled and deployed, from the execution, and from the execution until the state management, or you are trying to emit a result through the message. Now, let's look at this a little bit in depth, right? I went through the surface level, but what does it actually do? When the code will be released, there will be SDK crates that will be available to the developers that they will be able to see, the system level, the macros, and the SDK. So we'll go through the sys and the macro, but what is the SDK? The SDK also has 2 types of things: higher level system calls and on-chain collections. Now, higher level system calls can mean storing, retrieving from storage. It can mean printing. It can be events. On-chain collection, again, it's like utility functions. So how do you store? How to load this address from the VM, from the state? All these are on-chain collections that we also have, like primitives. Certain variables are already given to you, like integer, float, the character. You have various methods that are already existing in the SDK. So on-chain collections are templates that are already available for you to use. High-level system calls are what can be used to use these on-chain collections as well, if you from the surface level. Now, what is sys? This is not a sister, but the sys is basically 4 types. Think of a scenario where your processor and the developer. It would be amazing if I just sit in front of my processor and tell it what to do, right? And it does it. But it doesn't. So how does the developer or the computer now, let's say, talk to the processor? There are 4 ways to do that. Now, the first way is the register API. Second is the storage. Third is the context. And 4th is miscellaneous APIs. In the developer world, when we don't have a name for something, it's miscellaneous. Okay, so what is the register API and what does it do? Okay, now let's say when you're executing a contract, at that point in time, you are trying to send someone certain coins. When you try to send someone certain coins, we load the information from the database onto the register first, saying that Kevin has X balance, this person has Y balance. When this is loaded up in that specific register, it's an abstraction, saying that I am trying to abstract the storage. And the VM does not need to go back and forth between the storage. The register loads up the storage information and keeps it handy for the VM. I'll give you a small example. If you have ever used any apps on the phone, let's say you use, you're trying to read on Feedly, right? You open the app and you lock your phone from the home screen. You go back to the app, it opens up faster. The reason it opens up faster is because it's already loaded up in the register. Versus you close the app, force close it, and then you try to open it up again. It has to load from the memory and do it. So this is where the register APIs help the chain when the contract is getting executed to load information faster. We have the storage API. The storage API basically is saying that, I want to go and store this information onto the state. So the storage API allows a low-level system call to be made. Now, people can't make this call directly. Only a smart contract has the authority to do this. And this is where, what is the difference between a function and a smart contract? Like, why do I need a blockchain, right? I can just do it on a function, on a Web 2. The smart contract has explicit control over the database, but a function does not have that. You can bypass a function and go and change the database directly. Now, if you do that, the whole state tree, a state hash or the root hash is going to screw up. Sorry, but yeah, that's going to happen. But in a smart contract, it knows how to get this structure. So if you bypass a smart contract, the state will not update, meaning it is going to throw an error. So this is where smart contracts have, autonomy over things. Context API, right? So context API basically is more about input output. So, if you talk about the storage, that will go and store things. If you talk about register, that is loading things. So you load it first and then you store it. But what about things like I want to, be able to go and send, this information as an output to the console, or I want to output certain, or I want to take this value that I have received from a function onto a next function in a contract. That is where a context API can be used as well. Now, these are sometimes it can be like user provides these kind of arguments in the specified register, right? Now, what I mean by that is, if I say that you need to add two numbers, and these two numbers to be added are using some low level calls that, from the storage, it has to retrieve it, it has to add it. Now, the output of this is where context API comes, saying that this is my output, go and store it. So the context API can be used with the storage API together to go and provide an output and store it into the database. What is miscellaneous APIs? Like we have panic, for example. If you look at the transaction fee in the consensus architecture that I displayed, if you don't have the right fee limit, it will panic, it will drop the transaction. So this is where these kind of APIs help. So the VM can also know that I got to drop this transaction if this happens, or if there is an error, what to do, right? If it's taking more time in executing, what to do. Even message emitting are miscellaneous APIs in your logs that you have. So just a quick one here. When you actually, there is an output from a contract, it gets logged, and those logs are called events. So you can also add onto those logs, and those logs are always cheaper, as I mentioned previously. So you should only store things in your contract if you need to retrieve it afterwards. So if you're just adding two numbers and giving out the output, you don't need the output of everything that you gave. Then you don't need to store that output. You just emit that. And this is where miscellaneous APIs help you reduce the cost as well. Yep. Okay. Now, let's take an example of how the L1X VM and EVM interact together. So our L1X EVM is integrated with Hardhat. Hardhat is like a very simple tool to compile your contracts, run tests onto it, and deploy, right? So if you have a Solidity code, Hardhat allows you to compile, test, and deploy from the same place. So a lot of developers use Hardhat. If they're using Solidity, they will use Hardhat. So our L1X EVM works with Hardhat. We did the integration. It took like 4 months. We completed that. And we've got various RPC endpoints that are available that connect to the L1X EVM. So once you compile your contract or want to do a transaction on L1X EVM, use Hardhat. We have the RPC endpoints provided already, and you can interact with the L1X EVM. It's very straightforward. But how does the contract work, right? Maybe before that, let's look at this. There are three exact things that complete the L1X VM and EVM flow, right? You have to understand that for the database to be updated, it has to be independent of the VM that is trying to update it. So if I've got L1X VM versus EVM trying to update the same database, it has to do it in a similar way. Now, for it to be done in a similar way, we need a manager. And this manager helps us understand if a contract is being deployed through VM versus EVM, if a function is executed through VM versus EVM, what is those steps that I need to take in order to go and update the state. So we have something called as contract executor trait. And as I mentioned, there are 4 different types. We've got contract deployment, initialization, function, and read-only. Similar traits exist in L1X EVM, which is contract deployment and contract call. The contract call in L1X EVM for initialization and reading are the same right now. Now, if you have gone to the balancer pool and you try to preview and it fetches you the LP tokens, usually that should be a read call. But we have taken that as a function call at this stage. But when we launch, we will also have a read-only EVM call. So you will not have to make a transaction to go and read that information. For now, we have done that because we are still understanding in terms of the challenges we may face if we have different read-only calls through various state updates. So we are pretty close to implementing EVM read-only calls. Technically, it's not challenging. It's just timing that we need to test the systems and know when to release this. And we also have the execute module where, okay, if you are going and deploying a contract, which contract is this now? Okay, if you're saying deploy or initialize or function call versus deploy or function call from EVM, I get it. Is it an XTOC contract? Is it an EVM contract? Or is it an L1X VM contract? So based on your function of the manager, you can decide which contract type this is. So when somebody is going and trying to deploy this, we understand this is EVM contract rate, execute EVM contract deployment. So when this function is called, it goes and calls the execute contract EVM contract type. So this is how the node knows, okay, I get it, all right. Somebody's trying to deploy with this RPC endpoint. This is the function that is called EVM contract type. So this way we can go and deploy the contracts across different VM infrastructures. Now, what is the flow, right? So let's say we have a mint event that's happening. And this one, of course, we have the L1X VM. We have the L1X EVM. And what we are doing over here is we are trying to mint an ERC20 token based on the listener node or the XTOC contract. If someone has sent through some information or some tokens on Ethereum, and based on that, you want to mint it on L1X EVM, or you want to mint an NFT on L1X EVM, it receives a mint event. So the XTOC infrastructure will receive a mint event. It serializes the ERC20 contract method name and arguments. Now, what is this? It was the same one over here, this one. The arguments, it serializes it. Now, what serialization means is it makes it sure that the EVM can understand this call, because the XTOC language of function execution versus the EVM is different. So it serializes it for EVM. And we also have gone through the code for this in the XTOC AMA. It calls the contract in the L1X SDK function. Now, this is where the SDK comes in. So if you are trying to do a cross-contract call from XTOC to EVM, we have all these methods available in the SDK. You can simply just do a cross-contract call by putting the EVM contract address. And the call contract returns the result once we get the result. So on the SDK, we have a call contract, ERC20 address, and arguments. It goes into the contract executor. The contract executor understands, okay, the next task that I have is execute contract EVM. It takes that function with the arguments and executes it. Once EVM returns back the result, it gives it to the XTOC contract, and the XTOC contract can emit it. Now, there are two things to this. One is we are trying to control the flow of the EVM emission of the events through the L1X VM, but you can directly execute EVM and return the result. So there's nothing blocking you. The reason we have not done this directly as an event over here and we are passing it back is because if you execute this and the event fails, this contract does not know what to do next. So if the result comes back and you want to carry forward that information and emit it out, you have a completed transaction, because this is still one transaction, right? A cross-contract call. And if you just emit the event, this contract doesn't know when do I need to stop. Like, what's the next step? So our model is not having multiple controllers on multiple contracts. Our model is one controller contract and multiple sub-module contracts, meaning there is one contract always in control of what is happening, and the other contracts are responsible to do those things. Because let's say you had another contract here, which you were trying to call. Now, if these two contracts depended on each other's state, then who will provide this information? So if this contract returns back the state, we can take the same information and provide it here. So this always has the control of what's going on, allowing us for faster processing. Even the serialization functions are in one place. And that is where Xtalk contract helps us with that. Now, don't freak out, but I have something called as a contract executor. And yeah, please don't freak out. And the contract executor, so what I've done is our whole code base that we are going to release, each and every file and function that is responsible to do this activity. So what I just did over here, right? To do this activity, it's going through the Xtalk, L1X VM and EVM. What are the files that come into place one after the other? So these are all code, basically, right? All files. And these are the functions in there. So what files and what functions interact with each other to make this process happen? On the L1X VM, Xtalk and EVM instance for execution, I have put it up over here. So, and I will share this Miro board. So any developer coming in and saying, okay, if they want to do an audit, they want to check, they want to help improve the infrastructure, this flowchart was prepared for that. I only had an hour, so I couldn't make it simpler, but I think this is more than enough for any developer coming in and who wants to go function by function and see what is happening in this whole space. If there are memory leaks, how to improvise, or because someone like 80% of the Solidity developers have never looked at Ethereum code, right? And I can guarantee that. But if there are other parts of the developers who are interested and want to look at it, this is for them. Yeah. So I think it gives us a good understanding in terms of the compilation, the execution, L1X VM and EVM contract execution strategy, and even the execution manager's flowchart or responsibilities. I could get into this, right? But this gets pretty technical. Like I will have to go through each and every line of code and explain this, right? Otherwise, it will be a half-baked solution. But when we go through the opcode table and fee calculation in VM part 2, which is going to be a completely code deep dive on this execution manager, at that point in time, that flowchart will come in handy. Yeah.
That's fantastic. I suppose the question is, are there any questions? I know we've got a couple more that have come through as well. So I'll just, of course, Fur has a couple of really good questions, as he does. I'll just start up here and we can work backwards from top here. The VM is quite comprehensive and already has the capacity to decipher complex information into simple, efficient, and secure manner. Could the future version of VM also take over the EVM, or do the Solidity translations still need to happen at the EVM? This has possibly already been answered, but he would love a Kevin real-world analogy.
Yeah. So the question over here is that, when we have L1X VM and L1X EVM, can we remove the EVM and can L1X VM handle Solidity execution? Okay, two situations, right? We thought about this. First one is if you look at Neon EVM, right, and Aurora. So Neon is for Solana and Aurora is for Near protocol. It has a different consensus in itself, right? So if you want to execute Solidity code on Solana, you go through Neon. It has its own like consensus system, even Aurora. The problem is someone will build this on L1X, and then you have two different infrastructures running in parallel, right? Now, when we do see that developers are moving towards applications that require Xtalk and use the Rust code to develop contracts, the EVM definitely will go down, the requirement, right? But also to understand that EVM development through Solidity code is like JavaScript code. The syntax is very similar. There are more percentage of JavaScript developers than Rust developers, and that's the adoption thing. So at this stage, we do require the EVM, but later on, we may not need it because there is no thing that EVM does and L1X VM does not. Like the L1X VM does more than EVM, but this is just the adoption thing at this stage where we can't, like it just comes down to Solidity compilation. And L1X VM is not made for Solidity code; it's made for Rust code. So that would mean that you either change the architecture of the L1X VM or you keep it until the adoption comes through.
Excellent. So some of these questions are a bit back and forth in different directions, but we'll roll with them anyway. How can I get date of birth validated into my smart card?
Okay. That's a good one. So let's take 3 different steps to this, right? The first one is when you provide the information. The second one is when you confirm the information. And third one is when you're trying to retrieve it. Now, when your smart contract takes you as a wallet address holder or as an account address holder and provides that date of birth, right? It will link yourself to either a name in the same contract or to a name in another contract, right? The second one, you store this in terms where your name, your wallet address, and date of birth are in the contract. This contract can now be stored on a private DB or it can be stored directly on the L1X infrastructure, right? When you go and try to retrieve this information, right, you can do 2 things. One is you can build a function off chain to bring the date of birth, compare it, and then provide the result. Or what you can do is check. And then when you hit the check button, it goes and provides the date of birth to the contract. And the contract itself measures the time between the date of birth and the current date and provides you with a yes or no. So you can encrypt and store this information on the contract in a way and only provide a yes or no directly to the response that is being received.
Excellent. And like I said, they're a bit bouncing all over the place, but that's okay. Will testnet always be available to try out our own smart contracts?
Yes, definitely. And we'll do another AMA on the dev. So I'll personally be showing the development side of it as well. We have simplified it, completely. So there are 3 environments. One is your local net, one is the dev net, and one is the main net. So your local net basically is your computer. Your dev net will allow you to simulate the main net. Now, what is the difference between mainnet to devnet and local net to devnet? The difference is that, of course, you don't pay for actual L1X coins in the devnet between the mainnet and devnet. And between the local net and devnet, you can test it with multiple nodes. So we did a testing with multiple nodes across various regions, and we threw in tens of thousands of transactions, not to check the speed, but to check the accuracy. It worked. And according to the speed, when we have only L1X VM contracts being executed, we went to more than, I think, 80 or 90,000 transactions a second. But when L1X VM, Xtalk, and EVM are in place at the moment, we can do probably around 1/3 of that. But that's very quick if you think about it. You're going from VM to VM. And I don't think there is any other chain that has shown results of 2 VMs interacting with each other at that pace, even if you take Aurora and Near or Neon and Solar.
And can you elaborate on mechanisms in place to prevent double spending or other forms of fraud when conducting cross-chain transactions through the virtual machine?
Yeah. So in the VMs, there are two ways this is prevented. If you look at stack-based architecture, you have an accounts model where when you do a transaction, it waits. Regardless of your account is in place or not, it waits. In Solana, they have something called a C level, which is if your transaction is not in the queue, they let you go, meaning your balance is not impacted with the available transactions in place. Ours is more like the EVM. We have a clean mempool structure. So until your transaction does not receive finality, you can't process the other one. But again, is it only a transfer? Is it a smart contract update for L1X VM, or is it a smart contract update for L1X EVM? Because these three are three different things. Because if a smart contract activity is happening, that has a different cluster versus only transactions having different cluster. So, and it's very experimental. The Solana thing is very experimental because it's just 20 lines of code if you think about it, right? But if something goes wrong over there, your state root hash can get damaged, and that's why I also think that Solana faces a lot of downtime because of this experimentation. But in terms of the speed, I think having different clusters then changing the model of the account makes more sense.
Can we build on Bitcoin through an L2 like Polygon, or is Xtalk limited to only dApps built on L1X similar to Zeta or Omni dApps?
Yep, that's a good one. If someone comes and forks L1X VM, they can use Xtalk with that. So, and the beauty is you would be able to fork L1X EVM as well and use Xtalk with that. So in a way, you're building an interoperable EVM infrastructure only with your own consensus. So think about it: if tomorrow let's say Arbitrum, right? Arbitrum says that let's go interoperable. They integrate Xtalk and they can go interoperable, but they will have to change it to L1X VM. Now, if that happens, great, because still the Xtalk nodes are required, right? So event listener nodes are still required over there. How would you process it otherwise?
All works out. What was the biggest challenge you faced while developing L1X?
Where do I start? I think as I said previously, building a layer one is hard, but building an interoperable layer one out of Perth with the resources at hand, it's like an impossible task if you think about it. Like, it's so challenging. But look, I think the way I see things is it can be hard, but it's not. It can be impossible, but we don't know, right? And with layer one, the hardest thing was the whole architecture of it, because it's good and bad at the same time. It's like an ecosystem built so much for each other, right? Even if you remove like a single piece out of it, you don't know what's going to change. But when it's together, it works seamlessly. It makes it hard to fork it. Yeah, sure, you can fork the VM and use Xtalk, but then what about the different database drivers, right? What about the different contract types? So everything is built for each other for the ground up. I think that architecture definitely was very complex, because when we built the white paper, I remember having like a stack of white papers I was going through and drawing it, rubbing it back, drawing it, rubbing it back for like 8 months.
Yes, intensive work's gone into that, very obviously too, and I think Crypto Psycho can attest to that by trying to do a video series on debugging the white paper, and I think it's still going. So
It's still
big
going,
shout
yeah.
out to you, though. It's a monumentous task, and I think you're crushing it. This is definitely a question I think a lot of people probably ears perked up for, and it's: how did you manage to get the ex-head dev of Knox Samsung on board?
Yeah, so when I had a call with him, he's from Ukraine, and sometimes it's very hard to have a conversation with these type of developers, because for them there is no such thing as gray area. Now, it does make sense, I'm not going to do it, right? I explained to him so we were discussing about IoT devices taking over the responsibility of nodes in the future. We see a future where there are no nodes. It's just all decentralized everyday devices in place. And he thinks that is the future, but how to achieve that? So I kind of showed him some light on that. And this is what I think about it. So he wants to work where there is a future of complete decentralized infrastructures, and companies like like he was working for Near as well. So he was also he was responsible to build the account abstraction strategy at Near, and he did not want to continue because of the way decentralization worked at Near, and that's how I kind of brought him in. Now, do I think that is possible? Yeah, I think it's possible, but it's not practical, right? But did I have to say him to bring him on board? Yes, I did.
Awesome. And how will FVN data storage be different from boot nodes? If it's IPFS, like when does it mean it can be deleted if not maintained?
Yeah, it's a good one. Okay, so we have a whole, one more AMA should be done on that. Access control, version control, data and retention contracts, and decentralized IPFS data storage nodes technology already is there at layer one, right? Now, if you think about it, the full validator nodes will, without the ability to propose the blocks and vote, if IPFS database driver is attached to it, right, or the technology is attached to it, it becomes a decentralized IPFS node. So that configuration is available. Now, I definitely think that the challenge was this: when you upload database data on the blockchain, there is no such thing as delete, because a hacker or a person who wants to retrieve it can go back in time, right? So even if you try to remove the data from the chain at this particular stage, you go back in time to the snapshot and the data is still there, because the proof has to be there as well, right? Now, you can still keep the proof and delete the data, but then everybody else has to accept on that proof. So it's like a catch-22 situation as to, do you delete the data and the proof, or you only keep the proof over there? Because without the data, what use is the proof, right? The data existed. So at this stage, the IPFS technology that we are using allows you to encrypt the data and store it on the chain. And only your wallet address can be used to decrypt that information using the access control contracts. So without the access control contracts, storing data on the chain is not possible, where you are okay if everyone goes and reads that information.
So still on storage, thinking about on-chain level storage, will they store that in their own massive signer and broadcast a node cluster?
Is this the on-chain question?
Yes.
Yeah. So okay, the way on-chain wanted to build with us is, or go ahead with us, is that on-chain itself has forked Hyperledger Bezu, I think, which has the EVM compatibility to it, and they want to use the Xtalk access control and encryption infrastructure to take the identity data and store it on L1X, but the ID card will be on on-chain. But the ID card cannot be verified without the data stored on L1X. So that is what they are building.
And then last question in that lining, are you thinking of using near tricks to reduce, as in near the blockchain, near I assume, to reduce chain history size?
Yeah, well, I think I don't necessarily think that we need to reduce the chain history size for a few years, because this is what happens, right? You can create a configuration strategy where your backlog goes into like archive nodes and you store it in there versus your boot nodes. But at the same time, I'm not certain as to that's a good strategy, because this dividing data based on time may not be the ideal way. I think dividing data based on the frequently used activities can be something, but in blockchain, that's hard because you can't just divide certain data and store it somewhere else, right? In between the chunks, right? You got to move a whole block across. So clusters and the distribution of the node network can be a way of saying that I am pausing the block proposer role to maintain this information up to here, but the new blocks start again from the new nodes. You see? So you have these two data distributed based on the feature, but based on new nodes coming in.
And I think that effectively answers most questions. I mean, there's some here that are pretty out there, like, so today I can't run an FVM on my toaster. At this stage, no. But who knows? Who knows? We might get to that point. Maybe toasters will have the capabilities. Does L1X also have a hack team?
We did have we did have a hacker who worked with us, who wasn't registered with us but worked with us. But again, I think these audits are great. Like what Hashtag did, that was a very comprehensive audit, what they did for that part, right? Even the smart contract, great team. And the only way I see a hacker helping the protocol is misusing certain contract SDK that we have not seen yet. And we have tried and tested like various angles. Even the balancer contracts are there, the DGAL apps contracts are there, access control, username contracts, FT, NFT, XTOC swap, XTOC NFT contract. We have built everything, we have tried everything, it all works. Because if you look at the balancer contracts, it's like the most extreme version of contracts that you can deploy. And even that worked. And until now, it has not been hacked. Like, there are funds in there. I mean, hackers have gone for much less funds than that. So it has not been hacked yet. So I don't know. Maybe, we may need a professional like hacker team, but I think our devs right now, have a side personality of hacking. So I think we are using that while they're building it as well.
I think DD is going to have a conniption if I don't ask this question. When can we expect the Explorer?
Yeah, the Explorer is available in version 2. And if you want, I can just quickly, 1 second, let me see. Okay, let me just share my screen pretty quickly. Yeah, so the Explorer has come to version 2. You will get it in the version 2 itself. And these are like, we are still testing it without syncing all the nodes first. The nodes are still syncing, but all the transactions are here. So the total blocks, total transactions. So these are still in syncing state, but every information will be here. So it's still syncing though. So version 2, yeah, we'll launch the Explorer as well.
Awesome. I think that's every question actually. If there is anything that I've missed, guys, throw it in the comments now.
What's
that
that?
way
It's
catch me back up.
Kevin is also a hacker, right? No. No, I'm a certified ethical hacker. I'm not a not a black hat hacker. No.
Will we be able to search transactions like Polygon scan? Q transaction.
Yes. Yeah.
Yes.
That will happen. Yeah.
No, I think that's cleared the backlog of questions. Unless anybody can sneak any last ones in between. Is there anything that you want to wrap? Like, if you were to just envision that and go, okay, this is the wrap of that closing statement. How would you position that?
Yeah, look, I think on the infrastructure side, right, the virtual machine has, like, we have spent like more than a year on the building the VM from ground up. Just to give you an analogy, when people fork and do it as well, it takes like a year for them. And I don't know why they take a year when you're forking only. but building it up from scratch was a very time consuming process. We have tested it inside out. Hashlock audit will go through it on Monday. I was going to go through it today, but then we won't have anything to speak about on Monday and we would run out of time today. So the Hashlock audit also gives this out. We have the official report as well, which we will release it out to you with the version 2 update. You'll be able to go through the report as well. But more importantly, I think we have to understand that the network is being tested out right now. And the only thing I would say is that we need the nodes. Like I was saying this before as well. The VM is doing as it is. Like the VM was never a concern for me starting with. I was never ever concerned about the VM because I knew I could build it. But the ability for people to host nodes, that is concerning to me. I know it will happen, but when I say concerning, meaning I want 100% results, right? Like it should be perfect. So as long as the community and everyone else has the node hosting covered up, there is nothing to worry about from the technology standpoint. Like everything is working. Now, the only missing gap was the documentation. And in the next 10 days, we'll have that ready as well. And we'll do a separate AMA to show the developers how easy it's going to be to build with Xtalk and L1X.
Awesome. And so just one question before we go, because I saw this one asked in the community earlier as well, which I think is really pertinent to a lot of people that want to be able to, for example, track their transactions, do their tax, but all the fun stuff from going from the degen crypto back to the real world. Can we download a CSV data from the Explorer?
I can add that feature if you want, but what we are coming up with is a wallet profiler. So you just put in a wallet address and it will give you a whole profile of it. Balance, LP tokens, expert claims, nodes held by you, your transaction history for swaps, your transaction history for stake, balancer pool, gaming, any other application being built. So one single page for you. You may be able to export that. If you want that, drop down a comment. If you want to export your wallet profiler, I can build that in.
Yeah, so just throw a yes in the comments if that's something that sounds interesting to everybody. Let's read this. Yes, please. CSV. Can I use the term fintech when referring to L1X?
I would rather say that you can use the word account tech, because at the end of the day, it's ledger management in a multi-chain way. So you can use account tech. We are managing the ledgers for people. Yeah, but fintech, I don't think so, because, well, I mean, if you're looking at financial technology where you can navigate, explore, and transact digitally with Web3 for, just your financial aspect, but this is more than that. Like this is where I only have, I don't know how many more years to live, but I don't want to live under the assumption that technology is changing under the pretense of it. So I think this is more than just financial, right? This is like everyday thing. For example, what I did was to get an understanding on how the banking infrastructure works. I went and applied for loans to different banks just to test how it works. Every single bank is asking me for these documentation where I have an account with you for the last 4 years, and you still can't figure out, am I worthy of your credit or not? Like, you are going to tell me if I am worth the credit of my money in your account. It just doesn't make sense to me. So of course it's triumphing that aspect of things, but also on a day-to-day basis, it's gonna be able to help people out on so many different things.
I think the resounding answer for the CSV seemed to be yes, with the best comment being yes, make it a hamburger with the lot, Kev. Fair.
Yeah. What is Kevin going to work on after L1X? I have not even thought about it yet, because to be honest, we haven't even started with L1X yet. Like now it's like we have got pole position. I think suspicious someone built that graphics of L1X in an F1 car. Great job. We are still in pole position, but the race is still to go, right? So I don't know. Once we get L1X, to where we wanted to, then we will see about the remaining things.
Yeah, so the hot alpha there is we've just done the qualifying lap, everybody. Stay tuned. We are heaps more to go, heaps more. Yeah, I think that's pretty encompassing, and that's wrapped up a lot of stuff. Obviously, this is part 1 of 2 for the dive into the VM. So so many questions answered. I think once again, massive thanks from the community for taking that time to explain how everything works, what it looks like going through, what it looks like in the classic Kevin board. That's it helps, I think, from the front end of everything going on inside the community to understand, okay, how much more goes into this? How does it work? What does it look like from your perspective? And really help share the vision as well. So I think these have been excellent for helping press it out to the community. I suppose, yeah, one last question. Here we go. Is there any alpha for the community?
Yes. There is going to be an airdrop. I won't give you a number, but the last time we did an airdrop for a higher ceiling number, it's going to be somewhere around that, and it's going to have the public save vesting, 4 months vesting. So even if it is a 4-month vesting airdrop, it's going to be a higher number. And who is going to get that or how to participate in that, I think I'll let the marketing team say that, because otherwise they'll have no talking points on it. But yeah, that's one. And also, I will be making my public addresses in terms of the coins that are allocated to me public, so that, and you will be able to verify the coins that I should be allocated, and the wallet addresses of mine will be all public. So when I sell and when I don't sell. So that complete transparency will also be there with you all.
Awesome. Yeah, ask for alpha, get some alpha. No, that's fantastic. And I think a great closing statement from Kevin before as well. We'll look to wrap that up, obviously, knowing that we've got a part 2. We don't want to squeeze all the juice out. We can't dive into the hash lock stuff. We're too early for that. It's only a few more days. So let's wrap that there. So once again, thanks everybody for coming. Massive thanks to the community. You guys have really turned out and showed up to our lives for the last several weeks. And it's really starting to show that traction. Obviously, we're leading in. We're down under 20 days now to launch. So, things are starting to really ramp up, and it's really we're really about to kick off. So what I'm saying is thanks everybody for bearing with us for the time up until this point. But it's now go time. Under 20 days, and it's we couldn't be any more excited. I think that's it. You can see on Kevin's face how much it means, obviously. And let's all get behind it and send it to the moon, from pole.
Yeah.
Win the laps.
L1X wouldn't be what it is without the community it has. So thank you everyone for making it who it is. And one great thing is, wherever I go in Perth now, people kind of recognize, and I have the community to thank for that. I was amazed. Like, I did not expect it, but people do recognize, right? Layer 1X, like everybody knows about Layer 1X in Perth at least. So there's this Indian guy who's done it, and when they see me, it's like, you're the L1X guy. I said, and I take pride in it. It's like the community has pushed it so hard that it's on the face now. You can start to see that people are getting to know about this now.
You wait until we put the Kevin board on a board. Surely as a community team, we can make that happen. I'm sure that on launch day, that's something we can do, and I think that'll be hilarious. Anyway, we'll wrap that up. But once again, thanks everybody for coming. And we will see you on the next one. Have an amazing weekend, everybody. And good night, good morning, good afternoon, wherever it is, wherever you are. We're checking out. We'll see you very soon. Thanks, guys.